Welcome back. This is part 3 of our first science lab here at Kirtland Central High School. And we are at station number 4. This was where we were at the other day before we were so rudely interrupted by the principal getting on the intercom and telling us that we were about to be bombarded with a fire alarm test, which actually went on for about a half an hour. So it was a good thing we stopped. All right, station number 4. We have 4 balances here. We have a couple of dial-in balances, and then we have a triple beam, and then we have a double beam or a triple beam dial-in balance. But we're going to start here at number A. This one's been the finicky one all the time. Now, if you have not ever used one of these dial-in balances, we have a tens counterweight that we can move out. We have a hundreds counterweight that we can move out. And then to get our singles, let me come in a little closer here so you can see, we can dial in the numbers singularly. We go past the 0, 1, 2, and so on. Now this particular one, I'm going to try and zoom in here a little bit so you can see it. As you can see, there we go, coming into focus. On this one can give us 2 digits past the decimal point. And the way this works, and it is a little complicated, and you have to know how to do it, and I'm not quite that complicated, but we'll give it a try here. Let us assume for a moment that we had something on the scale, and it weighed in at 2 grams. 2 has gone past the 0. Then we have one more mark, so that would be 2.1. Well, it balanced right here, so how do we get that other digit past the decimal? Well, the way you do it is you just kind of follow these lines out, and where they exactly line up, that will be the number that goes past. So this will be 2.1, 0.11, 0.12, 0.13, 0.14, 0.15. So this would weigh 2.15 grams if we were doing that. But what we are indeed weighing is we're going to be weighing this. Let me zoom out here so you can actually see. We're going to be weighing this plastic D cup. Put it on the scale. And remember, using the balance, we're just going to throw this out here, 10, 20, it goes down, so we're going to run it back to 10. And then we're going to dial in the weight. There's 11, 12, 13, scales coming down, 14, 0.2, 0.3, 0.4, 0.5, 0.7, 0.8, 0.9, and let's call that done at 15 grams. So the D cup is 15 grams. We would record that on our lab sheet. Going back, we're going to now weigh a wooden block. The wooden block, we throw that on there. You just heard me do that. 10, 20 is too much. Come back to 10. And we're going to balance this at about 10. And 10.7 is about where that balance is at. So we're going to call the wooden block good at 10.7. We come around here to scale B. Now this one has been the smooth operator the entire time. Although right now the cold air has got it weighing just a little under. Let me see if I can adjust the adjustment there just a little bit to get it to come back into 0, which it did just right there. So we have 2 objects here. We have a magnifying glass and a magnet. The magnet goes on first. Now the magnet, let me just throw this all the way out, and no, that did not go down. So we'll throw this out to 100. We'll throw that out to 200. It does indeed come down, so let's go back to 100. And we're going to try 110, 120, 130, 140. It goes down at 140. So we'll back it up to 130, and now we'll dial it in. 131, 132, 33, 34, 35, 36. It's starting to come down, so let me move you over here so you can tell. 136.1, 2, 3, 4. And we'll see if that recovers. And let me back it up 1. And we'll call that good at 136.3 grams. 136.3. Now let me put the magnifying glass. It's just a regular old plastic magnifying glass there. We're going to put that on 10. 20 is too much, so we'll come back to 10, 11, 12, 13, 14, 15, 16, 17. Does it balance? Let's check. Not quite. 17.1. We'll call it good at 17.1. So there's the magnifying glass. Now let's work our way back around to the other side of the table so we can do the other part of number 4. This will be station 5. We'll come back to it in just a moment. So on C, this is the triple balance, and somebody left this. One rule, please, ladies and gentlemen. Never ever leave the balance setting like this. This will, over time, throw off the ability of your balance to come back to 0. And we like to leave them in that balanced 0 state. This one is balanced. Here we have two objects. Now this one works the same as the other. We have triple beam here. This one has been counterbalanced with the dial. So we can get this to work here. We have a steel cube. Steel cube goes on. Let's run this out. 100. 200, still up. 300, it comes down, so we'll run it back to 200. 210, 220, 230, 240, 250. It does drop, so we know it's somewhere between 240 and 250 grams. So now let's start looking at our dial in here. 241, 242, 243, 244, 245, 246, 247, and yes, we're getting close. 247.1, 247.2, 247.3, 247.4, and this is balanced out at 247.4 grams. So let's take this one off. Now, the other weight we have here, we have a counterbalance weight. This one actually goes to another scale that we do not have. And for this one, it says that it can be a 500-gram counterbalance, and that the actual weight is 147.5 grams. Well, let's just see if it is indeed 147.5 grams. So, there's 100, there's 200, it came down. There's 140, or there's 110, 120, 130, 140, 150, it does come down, so it is indeed between 140 and 150 grams. So now let's dial this in. 141, 142, 143, 144, 145, 146, 147. Now, I'm going to let you watch that. So it said it was 147.5 was the actual mass of this object. So 147.1, 147.2, 147.3, and we have zeroed it out at 147.3. So the number that is stamped on the top was indeed not an accurate number. 147.3 will be the official call. Now, if you'll recall from last year, this is our good friend, the triple beam balance. This was what we were used to using in the other school that I taught in. We have two objects here. We have an aluminum bar, and we have this plastic container. Plastic container is going on first. Now, I can tell that the plastic container does not have much mass. So I'm going to start back here on the tens. 10, 20, 30, it goes down at 30. So it is somewhere between 20 and 30. 21, 22, 23, 24, 25. We're not quite level. 25. 25.3, 25.4, 25.6, and as I look at that, that is really close. We'll call it good at 25.6 grams. Aluminum bar. Well, that was kind of a thunk. Let's see. 20, 10, 20, 30, 40, oh, it's between 30 and 40, okay. Between 30 and 40, 31, 32, 33, it's coming down, 33.1, 33.3, oh, so close, 33.4, 33.5. So the aluminum bar will weigh in at approximately 33.5 grams, and that is station number 4. The whole purpose of station number 4 was to give the students a chance to work on the different balances that we have and work with balances that are easy to use and work with balances that are a little more difficult to use. All right, station number 5. At this one, you were asked to read 2 thermometers. Now remember, we're using the Celsius scale. The first one says, what is the room temperature? So I'm going to put you up here, and it says, do not touch the thermometer. So as we zoom in, let's see if I can get you, there we go. This one, we're going to be using the scale on this side because that is the Centigrade scale. The F stands for Dr. Fahrenheit scale. And here you can see, let me get my handy dandy pointer out here, that on this one we are at 20 degrees Celsius, and then it goes 2, 4, 6, 8, 30. As I read this, we are at approximately 22 degrees Celsius or 72 degrees Fahrenheit. Now, the other thermometer asks you to please pick it up, hold it between your thumb and your forefinger, and then count to 30. What I'm going to do is I'm going to talk for approximately 30 seconds and just let you know that what we're doing here is the idea was for the students to see that yes, they can indeed manipulate and influence the data if they pick stuff up that they're not supposed to. Over on this thermometer, remember it is 22 degrees Celsius. Here I'm already up to almost 30 degrees Celsius, and I've only been jabbering on now for about 20 to 25 seconds. So we'll go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and after approximately 30 seconds, I've been able to raise the temperature of this thermometer to approximately 30 degrees Celsius. That is about 85 degrees Fahrenheit. So that is station number 5. And I'll just tell you, on this particular station, every time I've done this, after about 30 seconds, I personally can get the thermometer up to about 30 degrees C. In the classes, as we were reviewing the lab from the other day, we had some students that indicated they could get it to rise to about 34 degrees Celsius. Other students indicated they never got it above 25 degrees Celsius. So, quite a variation in the room when it comes to body temperature and your blood circulation, because I'm doing this under my thumb out at the end of my hand. Now, we come to station number 6. Station number 6 asks the learner, the student, to use the scale to determine the mass of the two objects, to place them in the beaker, and to record the change in the volume. We're doing a density calculation. So I have a beaker that's set at approximately 225 milliliters. I have a digital scale here, which I need to 0 because it's been setting here. And I have a brass counterweight from a real old-fashioned counterweight system. So we're going to set this brass counterweight here on the scale, and we're going to measure this in at approximately 197.89. We would round that up, and I have no problem with the student rounding it up to 198 grams. That makes it a much easier number to work with. So now what we're going to do is we're actually going to measure density. So the starting volume is approximately 225 milliliters of liquid. We're going to take the counterweight, place it into the liquid, and we're going to see that the volume changed upwards to 250 milliliters, or a change of 25 milliliters. Remember that to figure volume, the formula is, let me see if I can coordinate all my hands here, because I don't have my handy-dandy trusty tripod yet. Density equals mass divided by the change in volume. So density, and the actual unit of density is grams per milliliter. Density for us is going to be 198 divided by 25. If I pull out my handy-dandy calculator and I punch this data in after I make sure and turn it on, of course, we're going to do 198 divided by 25, and we're going to hit the equals, and we come up to 7.92. If we round that up, 7.92, we would get a density, a D, of 8. Or, what we're saying, if I understand my density correctly, let me get my handy-dandy dry cloth here. What we're saying is that this brass counterweight is 8 times, or 800% more dense than the water, because water, remember, has a density of 1 gram per milliliter. So this is 800%, 8 times more dense than that water that's in there. Now, the second thing I have is I have a wooden block, and as you can see, the block has been turning colors. By the end of the day yesterday, while it was wet, it was absorbing moisture. So we're going to weigh the block. Block weighs in at 16.96 grams, or 17 grams. This one's going to be a little more difficult. Go back to our 225 milliliters. We're going to put the block in. Now in this case, the block only rises about, I would call it, and I can't even see. Does it come up to the 250? Not quite. We have that meniscus layer in there, remember? So I would say that it rose approximately 15 milliliters. So 15 milliliter change, 17 grams. So now our formula again, let me flip my page over here so I can do this on the right spot. Fill this in for you. So our block measured at 17 grams. The volume was 225. We're going to call it 240 at the end, milliliters. Must keep our units. So the change in volume was 15 milliliters. And remember, D equals mass divided by volume. Now in this case, come on, clear for me, there we go. 17 divided by 15 is a mass of 1.13. 1.13, or 1 to 1. And as we look at that, the wood is indeed floating about half in, half out of the liquid. If the wooden block was floating all the way on top, much like your styrofoam cooler does when it blows into the lake, it would have a density that would be very low, 0.2 or something like that. If the wooden block was just at or under the surface of the water, we would probably give it a density of about 2. That's based on the calculations that we have here. So, density calculations, there we have it. Station number 7. Here's station number 7. We've had an issue with heterozygous, or not heterozygous, I think I'm biology right now. Heterogeneous and homogeneous mixtures. Alright, sample A. This is a bottle of man-made syrup. It has 9 ingredients on there. The only one that I think is natural is water. Everything else was made by man. But as we look at this container, we cannot see any of the individual ingredients that went into making this. This is a smooth-looking liquid. There's no particles floating. There's nothing but the bubble of air. So this would be a homogeneous mixture. It has got 9 ingredients. It is a mixture, and it is homogeneous. For sample B, this is potting soil. And as you can see, there are different sized particles. There's different colored particles. Heck, I don't even know what some of these particles are in this potting soil. But that is not all the same. It does not look all the same. Therefore, it is heterogeneous. The one that was on the test the other day had to do with Lucky Charms because they were using a cereal. Now, just to let you know, if all of the cereal were made up of these brown particles, it would be a homogeneous mix because all of the particles are the same color and approximately the same shape and size. But as we look, I can see other particles. I see other colors. I see other shapes. That is what makes this cereal a heterogeneous mix. And this last one, no, it is not what you think it is. This is simply water with some food color in it, but I cannot tell where the food color stops and where the water begins. If there was a layer of yellow on top and the clear water underneath, that would be heterogeneous. But because it is all one color, it becomes a homogeneous mix. And so this is station number 7. The final station is coming up in the next part, and we'll be back with that in just a moment.